Essentially, we're now entering our main synthesis part, and the approach we're going to take towards developing the coupling matrix design technique that I essentially introduced last time as our main goal here, our main design tool. So in our goal to reach that coupling matrix technique, we're going to start by reviewing some basic synthesis techniques. And I know that some of those are reviewed in undergraduate text, but they're quite incomplete, and I would like to make sure that all of you have an idea of how things work step by step. Even though, eventually we're going to be doing more things in the computational domain rather than analytics. So typically, when we start synthesizing a circuit to satisfy a transfer function, clearly the first step is to define the transfer function that we want. In a previous discussion, we talked about how one might select this type of transfer functions. They're primarily determined by characteristics related to amplitude and phase. And as I mentioned before, in this class, we're only going to be defining transfer functions based on amplitude. So essentially, it's the S21 as a function of frequency square that we are basically having here. The second step is to basically start from the S21 amplitude and essentially derive the S21 in the S domain. And the reason that this is an important step is because all the synthesis techniques exist as long as you know this parameter. And we have to do a couple of tricks to do that because, again, what we're really given is the S21 of j omega square amplitude, and from that we have to basically derive this part. Now, based on decades of research, specifically for lambda element filter synthesis, which is essentially where the story begins, this S21 in the S domain, in the complex frequency domain, essentially can be expressed as a ratio of two polynomials. The proof is something we're going to basically skip in this class, but it is basically guaranteed that you will have a polynomial in the numerator and a polynomial in the denominator, and each one of them obviously will have some roots. So the roots of the polynomial in the numerator essentially are the ones responsible for making S21 equal to 0, and they're basically called zeros. And the roots in the denominator are the ones for basically making S21 being infinity, and they're basically called poles. Now, it turns out that, and again, this is something we're going to basically skip in this class, is that these are Hurwitz polynomials, which essentially means that the poles of the S21 function must lie on the left-hand plane. And so one of the things we do know is that if you're going to make a stable system and you realize a stable system, you must choose the poles to be only on the left-hand plane. And this is important because as we're going from S21 square magnitude to S21, we will have choices. And so that's going to be one of the choices that we will make. On the other hand, zeros, we basically have far more flexibility. It turns out we can basically choose zeros both on the left-hand plane as well as on the right-hand plane. And which zeros you basically choose out of all the possibilities basically depends on whether you want to achieve an independent control of phase from magnitude. So it turns out that if you only choose the left-hand zeros, then you basically cannot control phase independently from magnitude. Once you choose the magnitude response, which will be something of this nature, then your phase is set. You can't do anything about that. And this is a well-known property. In fact, it turns out that for this case, the phase and the magnitude are actually related by a Hilbert transform. So once you know one, you basically know the other by simply taking a pair of a Hilbert transform. On the other hand, if you choose right-hand zeros, then you can actually control both of them independently. But the synthesis becomes more complicated. And so basically that's the trade-off. Now, you might say, from a physical point of view, when I realize a filter, what gives away if I have chosen left-hand zeros or right-hand zeros? And the issue is that the left-hand zeros are basically related to filters that have what we call the minimum phase. Essentially, what that means is that you have minimal phase from input to the output. And again, from a physical realization perspective, that means there is actually only, and let me erase this thing here, there is actually only a single path to go from input to output. So if you have a physical realization that guarantees that the signal can only go from the input port to the output port through a single path, then you basically have a guaranteed minimum phase realization, which means all the zeros are on the left-hand plane. So can you give you an example? Yes. So for example, if I synthesize a ladder network, so here's a ladder network. I'm only going to include 3 elements. So here's the input, here's the output. There's only a single path for the input to go to the output. That's a minimum phase. But if I realize essentially something that perhaps includes another path here, maybe it has another transmission line, maybe it has another transmission line, maybe here's another transmission line. So I include basically multiple paths, then basically I don't have minimum phase. So that's the easiest way when you inspect the structure to basically decide which of the two is happening. All right, so again, poles only on the left-hand plane necessarily. Zeros, you can be left or right depending on the desire. All right, now once we start from the S21 square magnitude, we must be able to, as I said before, synthesize this S21 in the complex domain. So the easiest way to do that is to basically write the magnitude as S21 multiplied with S21 complex conjugate, and then you analytically extend that in the S domain. The analytical extension is by writing down that S is equal to j omega, and therefore the complex conjugate here is realized by replacing j with negative j, which in the analytical continuation means you replace S with negative S. So if that's the case, then your numerator, which is written here, basically will be multiplication of the original f with the f of negative s. And similarly, you will have a very similar expression for the denominator. So this is just math showing how the expressions become once s is replaced, or once rather j omega is replaced by s. If you look at carefully those expressions, it turns out, and again, this is based on decades of theory of lumped element prototypes, that all your poles and zeros will come in pairs or in groups of 4. That means if you end up having a zero that is complex, let's say it will have the form of a plus b, then you will necessarily have the other 3 zeros as well. Or if you end up having a pole that is real, you will necessarily have its negative value. Similarly, if you have an imaginary pole or zero, you will have basically its negative as well. So if you have real or imaginary zeros or poles, you will have definitely a pair of them, and this is a necessity. If you have complex, you will have 4 of them. So that's where actually our choices begin, because as I mentioned before, we will choose only the poles that are basically lie on the left-hand plane and ignore the other ones in order to find out our function of S21 of S. So let me give you an example so you can see how this works. So let's suppose that we have chosen our Butterworth response, and our Butterworth response has the form that it's on right here. So as you can see, the numerator here is very simple. So the f of s, the polynomial in the numerator, is basically 0th order. It's just a constant. So there are basically no zeros. But the denominator is an nth polynomial. The g of s is right here. And if you do the process that I just described, so you go from the magnitude to the continuation in the s plane, then you just take this expression, you replace omega with s by j, and therefore you will basically get the expression shown right here. So basically the poles of this function here are going to be the roots of this polynomial down here. So let's see how this works. Let's say, for example, that our order is 1. So that means that now g of s is nothing else but 1 plus omega square. And clearly, when you replace omega by s divided by j, you will essentially get this polynomial here, which has 2 real roots. So again, notice that the roots come in pairs. And so we will have the negative 1 and the 1. These are the poles of the function, of the transfer function. We will only select the left-hand one. And that means that from the S21 square, we're able to go to the S21 of S by making sure that the root is only the negative 1. So I'm basically choosing the left-hand plane pole for my s to 1 function. So for the very simple case of n is equal to 1, you can see an explicit step going from the desired transfer function to the S-domain transfer function, which is once again what we need in order to synthesize the the circuit that implements that, as we'll see in later steps. Let's see one more example. So if my order is now equal to 2, then my g of s is 1 plus omega to the 4th. And that means I'm looking for the roots now of this polynomial. These roots are complex, so there are 4 of them. And clearly, again, I'm only going to choose the ones on the left-hand plane. And so that means that I will have now this Hurwitz polynomial that you will see right there. And here's one more example for omega for n equals 3. Now we have basically 1 minus s to the 6th is equal to 0. And we will end up having 3 roots in the left-hand plane. One is real, and the other ones are complex. And so the polynomial, again, is given from here.